All right, class. Well, welcome to this first virtual lecture for 120B. We're going to give this a shot and see how it works out. So definitely let me know via email how this works after I post it. If there are things that can be improved in trying to convey this sort of material in this media, let me know. What we're going to try to do today is use this Notability app so that I can actually work like I would work on the board, and hopefully my voice talking over these notes is sufficient to orient you to what we're talking about. So we're going to go and just dive right in like we would in a normal lecture. So, we've been talking about thermodynamics and the mathematical structure of thermodynamics. And one of the most important aspects of thermodynamics is this distinction that we can draw between two classes of variables, so-called extensive variables, of which things like the energy, volume, number of particles, or entropy are all good examples of. You reminded me of this, last Monday. Those are extensive variables, and what that means is that if I take two identical copies of a system, shown here in these two boxes, if I put those two identical copies together, I get a new system where those extensive properties, energy, volume, number of particles, entropy, for example, have all doubled. So I take two copies, I put them together, I get twice as much energy, for example. Those variables are to be contrasted with so-called intensive quantities, things like the temperature, the pressure, the density, or chemical potential. Those are quantities which thermodynamically, when I do this operation, putting together two identical copies, they remain the same. So if I put two systems with the same temperature in contact with each other, well, I get a system at that same temperature back out. So we would say that this action of combining two identical copies of a system that under such an operation, some properties add, those are the extensive properties, and others remain the same. That's what we mean by an intensive quantity. All right. Now this is kind of an odd thing, right? If I actually took these two systems, this system over here on the right and the system over here on the left, and I added them together, shouldn't they interact? If these were actually made of atoms and molecules, those atoms and molecules live on the boundaries. There should be an interaction between those new sets of molecules, and shouldn't that change the total energy? And the answer to that, and if the total energy changes, that means it wouldn't be additive in this simple way. But the solution to this is to acknowledge that it does, but only a really small amount. And the reason for that is those interactions are localized to a surface, and the surface is a vanishingly small part of a macroscopic system. So to a very good approximation for a macroscopic system, if I really do take two identical copies, I put them together, while in principle their energy just changed to be not simply additive, in practice, the deviation from the additivity is incredibly small. Which means that if we were to take, say, a system with energy E, which had twice the entropy, twice the volume, and twice the number of particles, well, that would be the same as having twice the energy of a system that has a single copy of the entropy, volume, and number of particles. So I take an extensive function like the energy, and if I add all of its extensive variables, entropy, volume, and number of particles, I'll get twice that extensive function back. Now I could play that operation in a different way. Imagine I have a system who has an energy where I fix the temperature, but now I put two identical copies of its volume and number of particles together. Well, I've doubled the system in both of the variables that determine its scale, the number of particles and the volume, keeping the intensive variables constant, then still leads me to this relationship that then I would have twice the energy of a system with constant temperature and a single copy of its volume and number of particles. Now, if I start mixing those two operations such that I change both intensive and extensive variables, then these sorts of simple relationships don't hold anymore. Imagine for concreteness, I take a system at twice the temperature, twice the volume, and twice the number of particles. That's not going to be equal to a system, twice a system, at some fixed temperature, volume, and number of particles. I change the temperature, I'm probably going to change the energy, and not in some simple additive way. Similarly, if I take a system at fixed temperature and I double the volume, keeping the number of particles fixed, well, then I change the density. I'm not going to have just twice the energy of some system at fixed temperature, volume, and that constant number of particles. So put very generically, the energy, which is a natural function of entropy, volume, and number of particles, if I take lambda copies of each one of those extensive variables, I will, through this extensive property, get lambda copies of the energy with a single unit of entropy, volume, and number of particles. Now, this relationship has a very well-defined mathematical structure. The fancy word for this is to say that energy is a so-called homogeneous function of order 1. Now that's a mouthful, but it's useful to note it because there are theorems associated with homogeneous functions. For example, Euler worked out for a homogeneous function that if, for example, f is a homogeneous function of its arguments x and y, such that lambda multiplying both x and y is equal to lambda multiplying f of x and y, just like our energy, then it follows that I could write the function f of x and y as how f changes with x at constant y times times x, plus how f changes with y at constant x times y. Now this is an exact expression for the function f of x and y, which is linear in x and y with prefactors that just determine how f changes with x and y. This only holds because f is a homogeneous function of order 1 in both of its variables. Similarly, if g is a homogeneous function of just x, though dependent on y as well, such that if I have lambda times x, I get lambda times g of x and y. That same theorem by Euler tells me that I can write g of x and y as simply how g changes with x, the sole variable it is homogeneous in, at constant y times x. So that affords a simplicity to the functions that are homogeneous in certain variables. For us, this actually gives us a way of writing down the energy in a simple way. So following Euler's theorem, this means that as energy is a homogeneous function of entropy, volume, and number of particles, it must be that entropy can then be written as how energy can be written as how the energy changes with entropy at fixed volume and number of particles times the entropy, plus how the energy changes with volume at fixed entropy and number of particles times the volume, plus how the energy changes with number of particles at fixed entropy, volume times the number of particles. That looks like a mouthful, but we know, for example, that how the energy changes with entropy is what we mean by the temperature. How the energy changes with the volume is what we mean by the pressure. And analogously, how the energy changes with particle number is the chemical potential. So now, following Euler, we can write the energy, note not the differential of the energy, but the actual energy, as linear in T times S minus P times V plus mu times N. So that's an integrated form of the energy, not the differential changes in the energy, which is now linear in all of our usual thermodynamic players. And if we wanted to write this slightly more generally, we could note that in general, we might have more species. So this would be a sum over particle identity, that chemical potential, times their particle number. Now this is a reasonably straightforward mathematical identity dealing with this homogeneous functions, physical origin being that energy is an extensive function as are entropy, volume, and number of particles. But it has a number of really important implications. So let's go through those now. The first is to compare what this linear relationship in the energy means to what we had previously from the first law. So if we compare with the first law, if we take, let's first remind ourselves what the first law was. The first law relates to changes in energy as heat, reversibly T ds, plus work, P dV plus mu dN, that this integrated form of the energy there says that if we take the total differential of the energy, well, that's equal to the total differential of Ts minus PV plus mu N. through the chain rule, this is going to generate a ton of terms. I'll have a t ds, but I'll also have a plus s dt. I'll have a minus p dv, but also a minus v dp. We have a plus mu dn, but we also have a plus n d mu. So the total differential of the energy given this integrated form up here now has a lot more terms to it. But comparing to the first law over here, it must mean that all of this is equal to 0, because we know the first law was correct. So it must be that s dt minus v dp plus n d mu equals 0. That actually gives us a new equation we haven't seen before. This equation here relates changes in temperature to changes in pressure and chemical potential. Most generally, again, if we had multiple species, we could have played the same game and we would have gotten s dt minus v dp plus some sum over different species n d mu, all of that equaling 0. This is known as the Gibbs-Duhem equation, as it relates changes in the potentials of heat flow, temperature, the potentials of volume flow, the pressure, and those of mass flow, the chemical potentials. That's really useful if we wanted to, for example, work out how derivatives involving two different potentials are related. That brings us to our second implication. Take, for example, how the chemical potential changes with temperature at fixed pressure. Well, if I have a one-component system, I'd look at this equation up here. Changes in chemical potential with temperature at fixed pressure. Well, that's quite simple. That's just minus the entropy over the number of particles. Similarly, from the Gibbs-Duhem equation, I could ask for how the chemical potential changed with pressure at fixed temperature. That's just going to be the volume over the number of particles, which is just 1 over the density. Now note that when we're manipulating this Gibbs-Duhem equation, these derivatives depend on fewer variables. Usually, when we looked at things like the first law or auxiliary functions, we had to keep a number of things constant as we ask for how one object changed relative to the other. Now, for example, how the chemical potential changes with pressure, we just have to keep one additional quantity constant, the temperature. This is because the Gibbs-Duhem equation essentially has gotten rid of the scale of the system. Over on the right-hand side, I have an intensive function, how the volume of the system divided by the number of particles, as I do on the left-hand side, a ratio of two intensive quantities. So the size of the system in this case is completely dropped out. These sorts of relationships allow us to, for example, convert equation of state information to, say, find the chemical potential. So an equation of state would be, for example, a relationship between the pressure and the density. And we can now convert that, because we know what we mean by how the chemical potential changes with pressure is just the density. We can invert this relationship to find the dependence of the chemical potential on the density. So let's actually do that for a system whose equation of state we know, say an ideal gas. So an ideal gas, you all know PV equals nRT. That little n is meant by the number of moles. R is the ideal gas constant. A much cooler way to write this is the number of particles. And instead of the number of moles times R, we have the number of molecules times kBT. If we rewrote this in terms of the density, we'd have beta P is equal to rho. So there's a relationship between pressure and density. This tells us that if we were to integrate the chemical potential using this equation up here, that the chemical potential at some pressure, say P2, and temperature T, less that the chemical potential of pressure 1 at that same temperature, will be equal to an integral over the pressure from P1 to P2, how that chemical potential changes with pressure if, for example, I fix the temperature. This Gibbs-Duhem equation, or this result from the Gibbs-Duhem equation, tells us what that derivative is. It's just 1 over the density. So if we scroll up, this is just equal to an integral P1, P2, 1 over the density, which depends on pressure through our equation of state. The equation of state relates the density to the pressure in a simple way. That's an integral from P1 to P2 of the pressure, 1 over beta P. And that's an integral we can do. That whole integral then, 1 over beta, gives us a factor of kBT. Integrating 1 over the pressure gives us log P that we evaluate from P1 to P2, which is then just equal to kBT log P2 over P1. Taking the difference of logs, you can write that as a ratio of logs. And again, because the pressure is linear in the density, this change in chemical potential could be rewritten as then just a ratio of densities, some rho 2 divided by rho 1. That tells us that for an ideal gas, there's a very simple relationship between the chemical potential and the density. Not the change in the chemical potential, but a chemical potential would be in general some constant plus kBT log the density. All right, so that's another consequence of extensivity, which let us get the Gibbs-Duhem equation relating potentials. It also helps us think about mixtures. So another application or implication of this structure would be to, for example, consider what happens if we have a system with mixed composition as we vary the composition. Imagining we fix the temperature and the pressure. So Gibbs do him would say that if we fix the temperature and the pressure from the previous result said that that must mean that if I sum over all the components, Ni d mu I, and fixed temperature and pressure, this must equal 0. Now imagine I have two components, a solvent will denote solve, and a solute denote sol. From this expression, it means that the number of solvent molecules times their change in chemical potential plus the number of solute particles times their change in chemical potential must be equal to 0, or rearranging in solve d mu solve must be equal to minus in sol d mu sol. Namely, the changes in the chemical potentials between the solvent and solute are related. If we define a mole fraction as the number of some component over the total, where the sum of all the fractions must be equal to 1. If we divide this through by n, I will have the mole fraction of solvent times its change in chemical potential is minus the mole fraction of the solute times its change, or bringing this over here, the change in the chemical potential of the solvent is minus the mole fraction of the solute over the mole fraction of the solvent, the minus sign, times the change in the chemical potential of the solute. The solvent, because we only have two components, its mole fraction is just 1 minus the mole fraction of the solute. And in the limit that the mole fraction is small of the solute, so we have a dilute solution, we can Taylor expand this function. 1 over 1 minus a small number to first order is just 1, which tells us that the chemical potential change of the solvent is then approximately just minus the mole fraction of the solute times its change in chemical potential. We will see that this relationship explains quite a lot of observed phenomena, things as disparate as why ice freezes when you put a little bit of salt on it, or why salty water boils at a slightly higher temperature. But that's getting ahead of ourselves. The last implication of this Gibbs-Duhem equation is in the definition of something called partial molar quantities. So essentially we've been playing around with the fact that the energy was a homogeneous function, which means that we could integrate it. And it was homogeneous because the energy physically is something which is extensive. Well, it's not the only extensive quantity, and therefore it's not the only homogeneous function. I could imagine looking at the volume of some system, which might depend on the temperature, the pressure, the number of components, say N1, and the number of type 2 species. Now, the n's are extensive, and if I double both n's at fixed t and p, I should double the volume. So this volume is a homogeneous function of N1 and N2, which means that by Euler, I can write the volume as how V changes with N1 at fixed N2 times N1, plus how the volume changes with N2 at fixed N1 times N2, temperature and pressure being held constant as well. This says that I can write the volume, total volume of the system, as something linear in the scale N1 and the scale N2. We'll define that coefficient, how the volume changes with N1, as V bar subscript 1. This is the partial molar volume. Namely, it's the amount that the volume changes as I add an infinitesimal amount of N1 to it. Namely, I can write the total volume as the partial molar volume of species 1 times how much species 1 I have, plus the partial molar volume of species 2 times how much of species 2 I have. Now, it's a good question what this means physically. One would be tempted, for example, to assert that it's the size of a particle, thereby thinking about how much size a particle takes up. If I add up all those sizes, I would get the total volume of the system. And that's right sometimes, but it's not always right. It's not always right because for example, imagine a gas. If I add one particle to a box, well, the density would change, but the volume per particles is really large. It doesn't change so much. It doesn't, and it probably has nothing to do with the size of that particle. So partial molar quantities are a little subtle. Partial molar volumes, in fact, don't even have to be positive. There's no reason, for example, that if I add some amount of N1 to a volume, that the volume of the system doesn't decrease. Right? So those are the sorts of things we'll explore a little bit more on Friday. Again, hopefully you are bearing with this presentation of the material. Hopefully it's clear. If it's not, if there are big problems with how we're doing this, I'm certainly open to changing the format within some reason. If I don't hear from any of you all, I'll assume that this was okay, and we'll do Friday's lecture in a synonymous way. Your GSIs are working actively to set up their own discussion sections and office hours, also Zoom compatible. And I think that they will have set up a place for you to upload your homework so that you can turn it in on Friday. All right. As is usual, I'll also upload notes, PDF notes with this lecture so that you can go over it at your leisure. All right. Well, thanks for tuning in.